Assalamu alaikum warahmatullahi wabarakatuh, and welcome everyone. This is the lecture of ion exchange within the course of Advanced Water and Wastewater Treatment. I am Dr. Muhammad Darwish, and we will start this video to explain some fundamentals and basics about the ion exchange as a treatment method used in water and wastewater treatment. So first of all, let's have some definitions and principles about ion exchange method. So what is ion exchange? So basically ion exchange is this displacement of one ion by another. Okay, so it's like exchanging ions which have the same charge from one medium to another medium. Okay, so the displaced ion is originally a part of an insoluble material. It can be solid or can be powder material. Okay, it can be particulate material. And the displacing ion is originally in solution, so that's the ion that we are going to remove. All right, so the exchanged ions, it must have the same charge, of course. So positive ions are exchanged for positive, and same goes for negative. So negative is exchanged for negative. For example, so the sodium is exchanged for magnesium, for calcium. The hydroxide, on the other hand, is exchanged for nitrate, for example. Okay, so this is one method to remove these metals and these ions from the water or wastewater. So the material that is going to exchange or is going to replace the ions is called the resin. Okay, so the exchange resin is either a naturally occurring material such as the zeolite, okay, or a synthetic organic material. It can be also synthetic organic material. So these resins is either cationic resins or anionic resins. Okay. For the cationic resins, they exchange cations, and for the anionic resins, they exchange anions. So the resins are usually beads or granule particles that having a size of about 0.1 to 1 millimeter. So it's small particles, but it is highly charged, or it contains charged molecules that can exchange or can replace the molecules existed in the solution. So for example, when we make softening for the water using ion exchange process, so we want to remove calcium and magnesium. Okay, so the target is to remove calcium and magnesium from the solution. The exchanger solid, it will release sodium ions, and it will replace the removed calcium and magnesium ions. So as we can see here, we have 2 RNA plus Ca. This will be exchanged with Ca and 2 Na. So the R is representing the insoluble part of the resin, which sometimes we call it the host. Okay, and the sodium is going to replace calcium. Calcium is in the solution, and at the end we have the resin, but already exchanged the calcium with sodium, and same goes to magnesium also. So this is only an example how exchange is taking place in the solution or in the water in order to remove the targeted ions. Okay, let's have a brief idea about the cationic resins and the anionic resins. So the cationic resins, those materials that have reactive groups, okay, they can give up or they can release positive ions to exchange other positive ions from the liquid phase. And same goes to the anionic resins, but using negative exchange ions. Okay, but what is the governing concept that will determine which anion will replace the other anion, or which cation will replace the other cation? There is something called the displacement series. Displacement series, okay, it is the governing concept that governs the exchange of ions. The displacement series, and also the strength of ions that will replace each other. So in that series that we can see here, you can see the barium, the lead, and all the other materials and all the other elements in a series. So, and also for the negative anions, you can see the sulfate, you can see the other anions, and ending with the hydroxide. Okay, so when an anion species is high in the series, which is like the barium or the lead, is in solution. So for example, if lead is in solution, okay, it can displace ion species in the insoluble material below it. So if the resin contains hydrogen or sodium, it can easily replace or exchange with lead and barium, magnesium, zinc, okay, because those are coming in the at the beginning of the series or coming before the hydrogen. So the hydrogen can replace all the cations that came before, and the more we go further from the hydrogen, the more is easy to make the exchange. So for example, exchanging zinc is not is somehow more difficult from exchanging barium, for example. So the most easier or the easier one is the barium, exchanging barium with hydrogen. And same goes to the anions. So hydroxide can replace, hydroxide in the resin, can replace any other anion in the solution. So if nitrate in the solution, it can be easily replaced with hydroxide. If carbonate, if bromium, so same goes to the same concept, okay, using the same concept, So the hydroxide will replace all the ions that came before, and hydrogen will replace all the ions or all the cations replaced or came before, okay. So as noted in this series, to remove any cation in solution, the displaceable cation must be the portion H+, and to remove any anion, the displaceable anion must be the hydroxyl ion, which is the OH-. So these are some shape of the resin. Of course, the resin particulate is like 1 millimeter, so it can be seen, it can be sensed and seen by naked eye. And this is holding the high charge or the molecules, either positive or negative molecules. So these are some example. Okay, this is anion resin, this is cation resin. You can see the shape, it's like a particulate material. So actually the resin inside, from inside, it is a network of cross-linked hydrocarbons attached to ionic groups. Okay, so you can see here the hydrocarbons, those negative charged, negatively charged exchange, those are the fixed anions, okay, and the fixed anions are connected to positive cations. You can see the small circles, those are the mobile, okay, or the positive that will be exchanged with the others. So the positive cations can be like sodium or hydrogen. Those can be exchanged with any cation already exists in the solution, like maybe magnesium or calcium. So from that we have different types of ion exchange resins. So the resins can be broadly classified as strong or weak, as strong or weak cation exchange and strong and weak base or anion exchangers. Okay, and this is also depending on the series, on the displacement series. So the resins that based on hydrogen, those are strong acid cationic exchangers, and the exchanger based on the hydroxyl group, this will be a strong base anions exchanger, based anion exchangers. Okay, now commercially, the first used commercially exchanger was zeolite. Zeolite is a naturally occurring porous sand, okay, and it was first used an ion exchanger used to soften waters. To remove hardness, to remove magnesium, to remove calcium, And we know hardness in water, it will prevent, or it will hinder the use of water, especially if you want to use it for washing and washing machines, or washing hands. The soap won't be working perfectly, and the water will not be so nice to taste or to use it. But these zeolites have been almost completely replaced now in recent years by synthetic organic exchange resins, and they have much higher ion exchange capacity since it is synthesized and it's manufactured, and it is more developed now rather than the natural zeolites. Okay, this is an example of a strongly acidic sulfonated polystyrene cation exchange resin. You can see the H group, or the H ions, is related to a long chain. This chain is called the host. Okay, this chain is called the host. So the host is holding the H ions, and the H ion will replace, or is going to replace inside the solution, is going to replace other positive ions, like maybe calcium, magnesium. Okay, and this is another example for a strongly basic quaternary ammonium anion exchange resin. So in this one, it is used to replace ammonium as the anion exchange, or the anion exchange group, and we can see the hydroxyl group related or attached to the host. Okay, so what are the uses or the main applications of ion exchange in water treatment? So first of all, the softening. Softening is a very famous and very popular treatment method of water, especially for drinking water. So the resin is used for softening is called the sodium exchanger. Why? Because it is used to remove the calcium and magnesium. So normally we use sodium exchanger because its sodium is released in the water. It won't be so much harmful like the others. And one of the most efficient exchangers used for softening is the sodium exchangers. The other use is demineralization, which means that removing the minerals from the water, or producing much pure water. Okay, and for this purpose, for this specific purpose, different resins are used, but the most thing is the hydrogen exchanger, which is the most used one. And this is used to remove the positively charged ions such as nickel, copper, sodium maybe. Yes, this is to demineralize, which means to pull out or to capture all the minerals and heavy metals included in the water to be able to use as a drinking water safely. And the second type is called the hydroxyl exchanger. Okay, so we have the cationic exchanger, which is the hydrogen exchanger, and we have the anionic exchanger, which is the hydroxyl exchanger. And this is used also to remove the negatively charged ions like the sulfates, the nitrates, bicarbonates, maybe chromates, okay, chloride. This is those negatively charged ions. They cause pollution to the water, especially nitrates and chlorides, and also some other metals. So this is the target, to remove and to demineralize and to purify the water for other uses. So let's have a look about some practical aspect related to the ion exchange. For ion exchange zone, for ion exchange, we have something called the active zone or the exchange zone. So if we have a column of ion exchanger, okay, because the ion exchanger is normally applied in columns, and the water feed will be from up here, okay, and it will flow down until it is purified inside the ion exchange process will take place inside the column, and then the water produced will be the purified water, and that, for example, will be at time equal t1. Okay, so here we have an exchange zone or active zone. So this zone in the blue color is considered the active zone, which means that there is no exchange happened inside the column except in this zone. So this is the zone that the exchange will take place. Okay, after a certain time, this zone will keep moving to the bottom, and the top layers will become exhausted. Okay, like this. The dashed layer is the exhausted one, and the active zone is moving downwards, okay, at t equal 2. But still we have a purified water because the active zone is still there, and the length is delta, so the length delta is not changing, and we still have enough resin or enough of the ion exchange column to treat. After a certain time, the active zone will keep moving downwards at time equal t3, for example, but at time equal t4, the delta of the active zone will become very less, and here we can say that the column is almost exhausted. Why? Because if the active zone is delta, so when delta becomes smaller, that means the water quality will become also less, and the efficiency of ion exchanger will become less. Why? Because the active zone became less and become more smaller. If we continue using this system, of course we will lose all the active zone and the whole exchanger will be exhausted, so we must go to another process to replace or to regenerate the ion exchange. So that is practically what happened in the ion exchange columns. It starts with higher efficiency and keep moving downwards until we reach the point of exhaustion, or before the point of exhaustion we have the point of breakthrough. So you can see here, this is another graph which shows the volume of water treated versus the effluent solute concentration. So first of all, at first using, so the delta is constant, and delta keep moving downwards until we reach a point which is called the breakthrough point. At this point, delta starts to decrease. I mean, the active zone, the active exchange zone, start to decrease, so the volume of water treated also start to decrease. Okay, and also the effluent solute concentration start to increase. Okay, it will start to increase the effluent solute concentration. So if the effluent solute concentration is like 0.1, which is a very acceptable limit, after breakthrough it will increase rapidly until it reach some concentration which is maybe equal to the effluent concentration. So that is the exhaustion of the ion exchanger. Okay, so this point is called the breakthrough point, which means that the ion exchanger is, I mean, the effluent quality is becoming less. Okay, so how do we calculate the distance or the depth of the ion exchange or the active zone of the ion exchange? Okay, so delta is the length of the active zone, and this long equation, of course, it has its own derivation, but we will not go into long derivation now. We just take the final equation. Okay, so this final equation, as you can see here are the parameters. The delta is the length of the active zone. Vx is the total volume of water or wastewater treated at complete exhaustion of bed. The bed, it means the whole the whole exchanger, which is called the bed. And VB is the volume of treated water at breakthrough point. C naught is the concentration of influent at delta. And V of n plus 1, which means the total volume treated at T equals n plus 1, like T equals 2, T equals 3, and so on. Vn is the total volume treated at the time n, okay? And Cn plus 1 is the concentration of solute at effluent of delta at time equals Tn plus 1. And same goes to the other. As is the superficial area of exchanger bed. Okay, so from here we can calculate the length of the active zone if we know all these parameters, and if we have an exchanger bed, so if we know the area, we know the row of water, of the product water, okay, and all of these parameters, if it is known, we can calculate the length of active zone of the ion exchange. Okay, there is one important concept related to the ion exchange, and it's also related to the carbon, to the activated carbon. So it is the same concept, which is called the regeneration. Regeneration means that at the point of breakthrough, we don't want to keep using the ion exchange until it is totally exhausted. At certain points, we have to stop using the ion exchanger and make something called regeneration, which means like the reproduction of the ion exchanger. So the resin beads, it attracts calcium, magnesium, and will release sodium. Okay, water, it has been softened now. Okay, but after vast number of calcium and magnesium ions that become attached to the resin, okay, and most of the sodium ions have been released to the resin, to release to the solution, so the resin can no longer soften the water efficiently, and this is called the breakthrough point, as we presented just now. Okay, so if we don't have any chemical reaction, new chemical reaction, the incoming calcium and magnesium ions, it will not be attached to the resin, and eventually it will be produced in the effluent. So the effluent quality will become less, and then we have to make a reverse process to drive or to pull out the calcium and magnesium ions of the resin beads and replace them with sodium ions. Okay, so this is the process of regeneration. We want to remove magnesium and calcium, which already attached to the beads, okay, or to the resin, and replace it back with sodium to make an active resin again can be reused in a second cycle of ion exchange process. So at appropriate time, the resin beads, it has to be washed with a strong solution, also known as the brine solution. So this solution is highly concentrated with sodium, okay, and that will cause the calcium and magnesium to be dissociated from the resin and replaced with sodium. But although the resin beads prefer calcium and magnesium ions, okay, the excessive concentration of sodium, this will overcome this affinity, okay, because the attachment of calcium and magnesium to the resins is very strong. What will make it to dissociate? It is the over concentration or the high concentration of sodium ions. This will overcome this affinity. Okay, so the calcium and magnesium are forced off of the resin beads and will be discharged to waste. And then the resin beads will be ready again to remove more calcium and more magnesium from the water. So we make reproduction of the resins. We prepare it again to be reused and recycled again. And the degree to which the resin is converted is dependent upon the concentration of sodium in the brine. So the more sodium in the brine solution, the regeneration solution, the washing solution, the more efficient regeneration that will result. Okay, let's have a brief idea about the ion exchange chemistry. First, talking about the sodium cation exchange. If we are talking about the process of softening, so the softening is to remove calcium and magnesium. This is the resin, and these are the sodium attached to the resin. So when the calcium is existed in solution and it is passed through the resin that holding sodium, so it will exchange calcium with sodium, and same goes to magnesium. In the regeneration process, for this kind of cation exchange, so we use a strong brine. Brine means a solution that contains high concentration of NaCl. Okay, it's a very salty concentration. Very salty solution. Okay, so the magnesium that is already now is attached to the resin, it will be treated with the brine, with the strong brine, and then will produce another, or will produce the resin. Once again, it will be attached to the sodium, and the magnesium will be released as magnesium chloride, then will be removed as a waste. And same goes to the calcium, also the same concept. So this is the sodium type ion exchange resin, and it shows how the sodium is released, and it will attach or attract other cations from the solution. Okay, how about the demineralization, the deionization? Okay, it is the same concept. However, we use the hydrogen cation exchange. So, for example, if we are removing calcium or sodium maybe from water in order to make it a very pure water, so we use a hydrogen cation exchange, and once the solution is passed through or treated with this exchange, so the resin will be attached and associated with the calcium, sodium, and other metals, and it will release hydrogen in the water. So how do we regenerate this kind of cation exchange? The regeneration will be using strong acid, not strong brine, it will be strong acid. So normally the acid is sulfuric acid, so the calcium that is already associated to the resin, it will be treated with sulfuric acid, and then we will have the final regenerated cation exchange resin already reproduced and ready for other use and for another cycle of treatment. Okay, now how about the demineralization or deionization of the anions? Same, we use the hydroxyl anion exchange. So the nitrate is treated with hydroxyl resin or hydroxyl anion exchange resin, and then the nitrate will be associated to the resin and release in the water the hydroxyl ions. And the regeneration is the reverse process. So the reverse process is using the strong base, and here we're using caustic soda. So the caustic soda is one of the strongest basic materials. So we just treat or dissolve, treat the resin that is already associated to the nitrate. So the nitrate will be released again as a waste, and the hydroxyl anion exchange, it will be reproduced and regenerated again. So this is just a schematic photo. It shows how the deionizing type of the ion exchange resin is working to attract the sodium, the calcium, okay, and releasing hydrogen in the water. So this is the basic, the brief of regeneration resins. Okay, we use acid if the resin exchanges hydrogen. We use brine if the resin exchanges sodium. We use caustic soda if the resin exchanges hydroxyl ions, and we can also use HCl, hydrochloric acid, if the resin exchanges chloride. Okay, so this is the regeneration concept that is related to the ion exchange process. Okay, now let's have an example related to the design of ion exchange and to the calculation of the length of the active zone. First of all, this example says we have a breakthrough experiment. This experiment is done in the lab to see where is the breakthrough point, okay, or when does it occur. So a breakthrough experiment is conducted for a wastewater producing the results below. Okay, so this is the table. It presents the result of the experiment. C is the initial concentration. Okay, C is the final concentration. C is the resultant concentration in the solute, and V is the treated volume of wastewater, okay, or of water. So we have to determine the length, delta, of the active zone. The diameter of the column is 2.5 centimeter, alright, and the packed density of the bed is 750 kilogram per meter cubic. So this is the rho P, packed density of the bed, of the resin. C node is the initial concentration of the wastewater, of the solute in wastewater, which is equals 2.2 milliequivalent per liter. And X over M is the ultimate exchange capacity, the ultimate treatment capacity of the resin. So here, each 1 milligram of the resin is able to exchange or to treat 6.5 milliequivalent from the solute. Okay, so at time equal 1, for example, maybe after such maybe 5 minutes, 10 minutes, okay, the final concentration was 0.06 and the volume was 1 liter. After that, the concentration increased to 0.08 and the volume was 1.2, and so on until we reach a volume of concentration which is almost equal to the initial concentration, which is 2.1, and the volume was 2 liter. But where is the breakthrough point? I mean, how much the length of the active zone here? Okay, so in order to know how much the active zone or the length of the active zone, we have to solve this equation. And this equation, it contains a summation here. So that means for each point we have to calculate the whole this parameter, okay, this this part of the equation. Okay, so we have to develop such a table to be able to calculate this part of the equation. We have C, we have V for each point of treatment, for each minute, or for each moment or period of time. Okay, so first of all, this part is Vn plus 1 minus Vn, which means that the second V minus the first V, and the third V minus the second V, and so on. So it will be calculated as 1.2 minus 1, which is 0.2, and 1.3 minus 1.2, which is 0.1, and you continue the whole column like this. The second part is Cn plus 1 plus Cn over 2. Cn plus 1, it is the second concentration, okay, compared to the first concentration, which is Cn. So this part is 0.8 plus 0.6 over 2, which is 0.7. Okay, and here is 0.09 plus 0.08 over 2, which is 0.085, and then you can continue the whole column as presented. And the last column is the final product of the summation. Okay, so just multiply those values and then we will have the final result, and then we can make a summation. Once we have the summation, it's fine, we can continue and solve the equation. But first we have to calculate the area, okay, because we have the diameter as a circle, So we can easily calculate the area equals by d square over 4, which is 0.00049 meter square. Okay, fine, we have all the parameters now. We can continue to solve the equation and find the length of the active zone, and here the active zone is only 1.2 millimeter. Okay, so only 1.2 millimeter of the column is active, and this active zone keep moving downwards until it is until the whole exchanger is exhausted.